All right, well, welcome. Sorry to start this a little bit late. I'm Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist here at the University of Hawaii Institute for Astronomy, Haleakala Division. And that's the talk for tonight. I hope you enjoyed it. Okay, no. But seriously, one of the things I do is I get to help put together these talks. And this month we have Kathleen Tatem. Did I say that right? Yeah. Oh, darn. I was hoping that was going to be my mistake for the introduction. So Kathleen holds a Bachelor of Science in Applied Physics with a minor in philosophy, as well as a Master's of Arts in the Philosophical Foundations of Physics. And these degrees are from Columbia University. She is working on her Master's and PhD in Physics at the University of Hawaii at Manoa. And she made a wrong turn somewhere and got associated with a guy that you all know by the name of Jeff Kuhn. And so Kathleen is working on him, working with him. We've all been working on Jeff for years. It's an ongoing project. It's no fun to make fun of Jeff when he's not here. He's, as you all know, he's a great guy, very brilliant. But she's working with Jeff, and she's working on helping develop new instruments for the solar telescope that's being built here on Haleakala, and I think most of you know about that. And so let's give Kathleen a nice round of applause. Okay, thank you. And see, I got my mistake in there. All right. Okay. And remember, go into the light.
Okay. Hopefully, I got this on right. Everyone can hear me. So thank you so much for coming out tonight. I'm really excited to be here and to be on Maui. I've only worked here for about 2 months now. So I've been on Oahu working on my PhD in physics, and recently came over here to work with Jeff. And, oh, louder? Oh. So there's no microphone. Oh, I think there, okay. So in case you didn't hear that, I'm working on a PhD in physics at UH Manoa, and I've come over here to work with Jeff Kuhn on the solar telescopes that are being built on Haleakala. And this talk advertised as Into the Light, constructing a solar telescope, meditating on time. These are some of my interests, and I'm also going to have half the talk be my background in physics and just an overview of physics for you. So a lot of that is going to be all tied together because it all involves light. And in some sense, I'm bringing my work into the light for you and everyone else who's watching this to know about it. And hopefully we'll all leave a bit enlightened, including me if you ask me challenging questions. So we're going to start with an overview of physics, some basic principles, and then we'll go through my past work, which is listed here, so pretty extensive. So just going through that, you'll get a kind of broad overview of current physics research. And then we'll get to the part which was advertised about solar physics and meditating on time. That's really going to be a poem on philosophy of physics, because one of my hobbies is creative writing, so prose or poetry. So that's how that happened. And then we can take questions over all these topics at the end. So I got into physics a long time ago. I was wandering in a bookstore in 8th grade when I came across a book called The Elegant Universe by Brian Greene. And this is what really first exposed me to physics. I didn't know too much about it, but I was totally captivated. I couldn't put it down. It was about superstrings and extra dimensions, really abstract philosophical concepts. And I was just amazed that we could study these things scientifically and work toward real answers to such profound questions. And I didn't actually get to take physics in high school. I went to County Vocational Technical High School, which is more to prepare students for the workforce. We have schools like that in Hawaii. And I was encouraged to go to community college. I majored in pre-engineering, so I was actually learning physics, but I didn't really know it then. It was titled engineering, a lot of machine shop work, motors, different thermal systems. And I really loved building things, working on robotics, and I just read about physics, and I really wanted to study it. And I ignored my teachers who suggested community college, and I applied to Columbia University, where I was accepted early. And I just knew that they did a lot of physics there. So that also made me the first in my family to go to college on both sides. My dad's from Bermuda, my mom's from near Philadelphia, which is where I grew up. And both my twin sister and I went to Columbia. And we were both the first in the history of our high school to go to an Ivy League school. So we were already breaking a lot of barriers just going to college. And right now I'm currently the only woman in the state of Hawaii studying a graduate degree in physics. So I've been a minority in a few senses, paving the way here. And I also didn't really know much physics when I came. So I was kind of one of the worst in physics in a bunch of disadvantaged students that came in my year. But as you'll see, I've done a lot in physics ever since. So when I first got to Columbia, I realized that Brian Green actually works there. I had my book on my shelf, and a friend saw it. He was like, "Oh, he's in New York." I was just so amazed that maybe I could get him to sign my book. And actually, I ended up taking a whole year of classes with him. So that was really pretty beyond my wildest dreams. And I also worked in a really cool lab, shown here, and I built lots of physics apparatuses. So there's a Tesla coil, actually makes lightning in the room. So I had a lot of fun building stuff, and I realized that you can basically do all the fun things of engineering while doing physics, but you can build things to answer these really profound questions. So this is what got me into experimental physics, and I've been doing it ever since my first year of college. So we're going to go through our overview of physics. So I'm going to start with the question of what is light, and I thought maybe people from the audience might want to make suggestions here. Any maybe people know already because they come to these talks a lot, or electromagnetic radiation.
That's quantized.
Any
An
other
excitation in the electromagnetic field within certain wavelengths.
an excitation of electromagnetic field within certain wavelengths. Okay, good. So there's more than one answer.
Particles that behave like waves.
Particles that behave like waves, also true. So yeah, it took physicists a few centuries to figure this out. So good job here. And yep, like someone said, light is an electromagnetic wave. Of course, if you don't know what an electromagnetic wave is, this doesn't really mean anything to you. So this was something that fascinated me when I was in high school studying motors. They talked about electromagnetic induction. They didn't really have a physics class to tell me what exactly that meant. But basically, an electromagnetic wave is electric fields and magnetic fields inducing each other. Like any wave, you can associate a wavelength with it, the difference, distance between the two peaks. So we have all kinds of information in these waves. And really, they're come from electric and magnetic fields. So we know that charged particles have either a positive or negative charge. They have an electric field around them. And for magnets, they have their own magnetic field. And it was realized that these forces are the same as one electromagnetic force. Experiments in the 1800s showed that if you have a changing electric field, it creates a magnetic field. And if you have a changing magnetic field, it creates an electric field. So basically, when you have one changing, it creates the next one, but as it's being created, it's changing. So this is how we have propagation of electromagnetic waves. And it wasn't realized that this is light until it was studied what's the speed of these waves, and it was realized that independently test for the speed of light, these were the same. So this is how it was realized that light is an electromagnetic wave. And it has a whole spectrum. So all the different wavelengths or frequencies, these are what creates the different colors that we see. So there's a band there that's highlighted. This is the optical wavelengths, all our colors. And you've heard of X-rays, microwaves, radio waves. These are all electromagnetic waves at different frequencies. And higher frequency means shorter wavelength. So that sort of thing. As other intro physics, the world is made of atoms. So everything's made of atoms that we know of, like ourselves. We have a periodic table of elements, which is basically just categorizing different types of atoms. Atoms are made of protons, neutrons, and electrons. And there's a nucleus of the protons and neutrons. So these are positive charges, neutrally charged, electrically charged, no electric charge basically for the neutron, and then the electron surrounding them. And the periodic table comes about from different combinations of neutrons and protons in the nucleus. But this is what we believe to be fundamental, but we have an even more fundamental table called the Standard Model of Particle Physics. So the first column there, the up part, the down part, the quarks are what make up the protons and the neutrons. So they used to be considered fundamental particles, but they're actually divisible into 3 different quarks, and only the 2 in the first column there. So different combinations make the neutron, and different combinations make the proton and other types of particles. The electron is fundamental, and then there's 3 other columns there that are matching colors. Those are basically heavier versions of those particles. So they don't make up atoms, but they are passing through us from outer space right now. There's also a row there of neutrinos. So those are electrically neutral particles, and they're really tiny and really fast, and they're hard to detect. And then there's bosons there, which are particles that mediate forces. So there are 4 fundamental forces in physics. One we talked about is electromagnetism. And there's also 2 nuclear forces and the force of gravity. So gravity is pretty weak in comparison to electromagnetism. Electromagnetism dominates almost everything we experience, things like light, friction, the fact that we're not falling to the center of the Earth right now, despite Earth's gravity. These are all due to electromagnetism. And there's a few theories of physics, main theories. So we have quantum mechanics, which describes very small scale of atoms, subatomic particles. Classical physics, this is physics that explains our everyday life, and also general relativity, invented by Einstein, so to explain large-scale phenomena, astrophysical phenomena. And both general relativity can make sense of what we experience in our scale, and so can quantum mechanics, but they don't work well together. So a big problem in physics that we don't have a quantum theory of gravity. Because you can't see everything on the slide. So there's a few big problems in physics that I've listed. One is that we don't have a quantum theory of gravity. We don't have a dynamical explanation for quantum measurements. And we also don't know what 95% of the universe is made of. So this is called dark energy and dark matter. So these are just some big questions that I find really interesting and motivate some of my research. And there is another description of light. So I said there's more than one right answer. You could also say light is a photon, which is the particle description of light. And someone mentioned that it's a particle and a wave. So this was learned from Einstein's interpretation of experiments that showed light knocking electrons off of the surface when it was shining on it. And this is what won Einstein the Nobel Prize, the photoelectric effect. And this is something we use all the time in physics experiments because the momentum of the light is being transferred to electrons, and this is how you can produce an electrical current, so an electrical signal that we can use to study what's going on. And there's some fundamental ways that light is produced. So you might think of different sources of light, like the sun or a light bulb, but really fundamentally, there's different ways it can happen. So atomic transitions. So there's electrons surrounding the nucleus, but they can be at different energies. And when they lose energy, the atom will emit a photon, so it'll emit light, but the light will be the difference between the energy states of the electron. And this is something we use a lot in astronomy, because the electrons can only be at certain energy states, the light can only be emitted at certain energies, and also the energy of light, quantum mechanically, we know it can only have a certain frequency associated with it. So by looking at where it falls in the electromagnetic spectrum, we can know what the energy of light is. And based on energy, we can know what atomic transition produce the light. And because there was only certain quantities of energy allowed, this is why it's called quantum mechanics. Because it doesn't take on continuous values, only certain values. And there's other ways, so particles that are accelerating, that are charged, and if they're slowing down, they'll lose energy and they'll emit light as radiation. And particles that are decaying into less massive particles. So a lot of times when little fundamental processes are losing energy, a photon will be emitted. So this is why light is a very useful study, because we can use it to infer what produced it, and then hence study that. So one of my first things I did in the research laboratory was working with telescope spectrographs. So this is a diagram of a spectrograph here. So I built one, and I made a guider, so something that will shine light from the telescope into the spectrograph, and took some spectra of stars in New York City just to test it out. So, and this is something we use here at the NTRC a lot, so this is also useful for later. Light comes in through a slit, and then we send the light to basically something like a prism. And if you've ever seen a prism, you know that there's lots of a rainbow of colors. So what it's doing is splitting the light up into different wavelengths. And then we shine this onto a detector, basically a digital camera, and we get a picture of the slit, but at different wavelengths. So we see spectral lines. And this is what we use in astronomy to figure out what kinds of atomic transitions are producing the light. So you might see all kinds of news articles that say, oh, there's helium in this star or something, but obviously no one's been there. We know this because we look at the spectrum of the light using a spectrograph. It's a very useful tool in astronomy. My next work was in plasma physics. This is a picture of the laboratory where I worked. It was actually a scene in a Spider-Man movie filmed here, because it's a pretty mad sciencey place. So you've probably heard of 3 phases of matter: solids, liquids, and gases. But there's a 4th phase called plasma. So as you know from experience, as things get hotter, like water, ice, it's solid, then it becomes liquid, then it gas as you keep heating it, as it evaporates. What if you kept heating it? Eventually it would become a plasma. So that's really ions. Like the electrons are stripped apart from the nuclei of the atoms. So you have an electromagnetic fluid. So the gases and liquids, they'll flow, but the plasma will flow as well, and it's going to be more complicated because it's electromagnetic. So it'll have its own electromagnetic fields, and it'll respond to surrounding electromagnetic fields. So we magnetically confine this plasma. And this is a process that happens in the sun. Basically, the goal of this work is to produce fusion on Earth as an alternative energy source. I did a few experiments here. So one was to study optical light coming from the tokamak. This is called the tokamak, if I didn't mention it. That's an acronym for a Russian word where it was invented. And basically used optical light to study what kind of transitions are occurring inside the tokamak when the plasma is breaking down. And another experiment was we wanted to know where the plasma is hitting the walls when it breaks down. So again, I was looking for light, looking for X-rays that come from accelerating electrons when they're coming close to the walls. So that's something we did to study the plasma. Again, basically what we're detecting, light. So I worked in plasma physics for about a year, but during that time we also studied abroad in Australia at the University of Queensland in Brisbane. And I worked in a research laboratory on quantum optomechanics. And I was a sophomore in college, so I had no idea what this meant. And I just read enough to know that it was going to be pushing the boundaries of quantum mechanics as far as they wanted to get a massive object in a quantum state. So I felt really fascinated. And my friend was like, are you really going to go talk to that professor? Like, do you actually know what that's about? And I was like, no, but I talked to him anyway. he talked to me for about a half hour and asked if I knew anything he said, and I was like, no. But he was like, you can still work with us. So I got to work in their lab and basically just followed as a graduate student around and helped design a circuit that will cool this thing down. So the idea is that this is a fiber optic, but it's in a shape of a toroid. So it's really microscopic, but it's definitely a lot bigger than atoms that are usually in a quantum state. And the oscillations of the light inside the fiber optic couple to the vibrations of this toroid. So because the light has quantized oscillations, the vibrations, the mechanical vibrations of the toroid are also quantized. So this is really hard to achieve because of thermal vibrations, surrounding thermal vibrations. Basically in physics we understand heat as lots of oscillations of particles. So the hotter something is, the more things are jostling around. So we were working on trying to cool this thing down so that you could kind of push the limit of what we can put into a quantized state. So really awesome. And I kept thinking about quantum mechanics, and I heard a talk on neutrino oscillations, which is a quantum mechanical effect, also something I had never heard of. And I decided to join this research group, and I went to the Fermi lab during the summer. That's a picture of me and the group there and something we worked on. They're building a detector called microboon, which is basically a big tin of argon and a lot of wires and detectors of light to look for light coming from neutrino interactions inside the tank of argon. So neutrinos interacting with the argon nuclei. And these neutrinos are produced at Fermi Lab, which has particle accelerators. It's called Fermi National Accelerator Laboratory in Illinois. And the goal was to really study the oscillations of neutrinos, which is a quantum mechanical effect. So there's 3 types of neutrinos, if you remember that standard model of particle physics, the 3 columns. So there's some that are heavier than the others. Basically, we don't really ever get to detect a neutrino directly. They pass through everything, and they're passing through us right now all the time. I've heard that if you could see neutrinos, you would not be able to see anything else ever. That's how many of them are around us all the time. But they pass through atoms very easily because atoms are very small. Like the nucleus is extremely small, and they don't interact with the electrons or the protons electromagnetically. So they stream through atoms because they're mostly in space. So you need a lot of argon and nuclei to get enough interactions, because they interact with the nucleus via the nuclear forces. So that's the only way to stop them. And the goal of detecting them is really just look at things that come out of that nuclear interaction. So it was found that when you know what kind of neutrinos you're sending out, because you know how to produce them as well, find that farther away, they actually change type. So when they're when it's called an electron neutrino, it produces an electron. If it's a muon neutrino, a muon is produced in the interaction. Same for the tau. That's how we know the type. So it was found that they oscillate, and there's a theory to explain that. And then it was found that they oscillated over shorter distances than the theory explained. So microboon was set up to try to confirm these experimental results. So one idea is that maybe there's a 4th type of neutrino that they're oscillating into. So this research had the potential to basically add another column to that standard model of particle physics. So I found this to be really exciting. And because the quantum state of the neutrinos is kind of up in the air until they're detected, we don't know how they're going to oscillate. This is another way to try to understand the dynamics of quantum measurements. So this is why I found that research really fascinating. And what I was doing basically is a lot of electronics work. So using photomultiplier tubes, something that uses the photoelectric effect to create an electrical signal from light coming from the interactions in the tank of argon. And my work was basically to write code to analyze the raw signals and turn it into something useful, and to run tests of this whole system for the light inside the argon tank.
And this was after I graduated college. I worked on the LIGO experiment, which is the Laser Interferometer Gravitational Wave Observatory. So this is something that was awarded the Nobel Prize for the theoretical work behind this experiment. This experiment is aiming to make direct detections of gravitational waves, which they've done at this point. So Einstein's theory of general relativity predicts gravitational waves. So unlike light that's propagating through space, or sound that's propagating through air, water waves, gravitational waves are space-time itself basically expanding and contracting and carrying away energy. So from really cataclysmic astronomical events, energy can be carried away as gravitational waves. And the way to detect them directly is to look for expansion or contraction of space itself. So this interferometer is basically really sensitive to measuring distances. So this again uses light. So there's lasers sent out split into two different beams, and we know the speed of light, and we know the timing of when things are received, and everything is kept as stable as it can be, so we know extremely well the distances. So as you have waves traveling forward and when traveling back, they can interfere. So you can just think of it as sometimes the peaks of the waves will be together and it'll become a bigger wave, or sometimes they'll totally cancel each other out, or anything in between. So that's the interference of the waves, and that can be used to tell really precisely what the distances are along these beam lines to see space itself expanded or contracted. So what I did was build a magnetometer, so something that detects really low frequency changes in magnetic field to go into the mirrors, because we want to be, really, these mirrors have to be really sensitive. Everything needs to be aligned very carefully for this to work. So a lot of these experiments, I'm always building stuff and then also testing it out. After that, I worked in biophysics. So there's me in the biophysics lab, standing next to my professor, who was the inventor of the highest resolution atomic force microscope in the world, which is next to me on the table. It's really tiny, and then there's a regular microscope next to it. So we use this to, I collected data that's going to basically be published sometime soon in Nature Materials, so I won't give away too much of what that is about, but we have a mathematical model to explain intercellular forces and how they affect cell geometry. And we have this at the really high resolution, so basically at the level of molecules. So this research is helping advance biology, really, because we're getting mechanical understanding of cells that are only understood at a chemical level right now. So the idea of an atomic force microscope is basically that instead of having light bounce off of something inside a regular microscope, you just actually have something bounce on top of the thing we're looking at, basically just poking it and seeing how hard or soft it is. That's the basic idea. And usually they just bounce up and down, but what makes it really high resolution is that it has a little T shape, so it kind of bounces side to side, and that side to side motion is really fast, so it ends up poking the cell a lot more frequently. So that's how we get a lot more detailed data. And using this thing was kind of like driving a car, maybe, because you had to be really careful not to hit anything, because if you hit the cell, you could damage the cell, or you could damage this really sensitive to focus microscope. So it was definitely a bit tedious and challenging, but I actually collected enough data to confirm my hypothesis. That was really awesome. And while I was working there, they asked if I would want to work extra hours to hand pipette some biological ink that someone else was using. And I thought, that sounds really tedious and boring, but I said I would help them make a mechanism that could do that. So I built this device pictured here, which is the 3D bioprinter, which prints biological engines. So the ink that it was using is basically made of a solution of bacteria spores, and they expand and contract around water vapor. So this is like an experimental alternative energy source. So they use it to make little kind of toy cars move or something right now. But by varying the water vapor level, they expand a lot and then can contract. So you basically have a little mechanical drive system using these spores. And this thing is basically a milling machine, if you're familiar with that, but it's like designed to have a cutting tool to carve out different shapes in 3 dimensions. So I use that and then attached a printhead to it and sync it up electronically and optimize it to print this biological ink. And they're still using it now. After that, I worked on the fireball experiment. So this is in the field of particle astrophysics, which is basically astrophysics, but also trying to study particles. So this experiment aims to look for a source of dark matter. So 95% of the universe, we don't know what it is, we just see gravitational effects with this energy and mass. And there's some theories that maybe part of that dark matter is some normal matter. And this balloon experiment is going to look for ultraviolet light that could be coming from the intergalactic medium if there's normal matter there. So looking for light from molecular interactions from atoms, and that if it's there in the intergalactic medium, this could be an explanation for some of the dark matter problems. So I just helped with testing out different components and designing different components that went into this. And this is some of my work in Hawaii before I came over here to the ATRC. This is the Antarctic Impulse Transient Antenna, the ANITA experiment. So those white things there, those are antennas, and they look for radio waves. And this is also a balloon that goes, is sent above the atmosphere. But instead of looking into outer space, it actually looks down at the Earth. So the Antarctic ice is our neutrino detector. So it's kind of like the microballoon experiment I mentioned, except the neutrinos are coming from outer space, and the detector is the ice. And here's a diagram of how the radio waves are produced. So I mentioned there's more ways that light can be produced. And you've probably heard that nothing can travel faster than the speed of light, but this isn't true generally. Light can slow down in different media, so in air or in water or in ice, light actually travels less than the speed of light in vacuum. But we're looking for neutrinos, which are really tiny and they travel at close to the speed of light. So in the ice, the neutrinos are actually faster than the light. And you can kind of make sense of this because light's an electromagnetic wave, and all the atoms have electric fields around them, so this kind of slows down the propagation of the light. So you can see there's a diagram of what happens when there's just not enough time for the fields to just expand around, and you get a light cone called the Cherenkov light, and this is the radio light that we look for with our antenna coming from the ice. This is how we look for these really high energy neutrino interactions. And the reason we're looking for them from outer space is because there's a limit to how much energy you can produce in particle accelerators in the laboratory, but there's super high energy particles in outer space. So we're looking for the neutrinos, which haven't really been deflected by anything because they pass through almost everything, to try to study fundamental, really, really high energy fundamental physics, particle physics interactions that only happen in outer space. So that's a big motivating goal. And eventually there's also the hope that you can use neutrinos or other cosmic ray particles to do astrophysics. So regular telescopes, we look at light coming from objects in outer space. The idea of particle astrophysics is both to learn about particle physics that we can't do on Earth, and maybe to use these particles instead of light and telescopes to do astrophysics. So this brings us to where I am now. This is the Inouye Solar Telescope on the summit, the tall one there. So this is what I'm working on here for the last 2 months. And this is a diagram of the inside of it. There's a lot of instruments that are going inside this thing. And I'm working on the one that's called the cryo-NIRS. So this is what you saw in the flyer. And the cryo-NIRS stands for Cryogenic Near-Infrared Spectropolarimeter. So that's probably a bit overwhelming sounding. So I'll help break down what it does just using the name. So cryogenic means we want to keep it cold. I mentioned thermal vibrations, so it's usually good to have experiments very cold because you don't want extra signals in your camera because of thermal noise. Near infrared means looking at the near infrared region of the electromagnetic spectrum. And a spectropolarimeter is basically a spectrograph, but it has a polarizer in front of it. And a polarizer is basically what your sunglasses are. So it blocks out certain polarizations of light. Light's an electromagnetic wave, so there's electric field and magnetic field that's propagating forward. So the orientation of those fields has its polarization. So if you have slits blocking certain directions, only light of certain polarizations will be allowed through, basically, the polarizer, just basically like sunglasses. And in that way, if it has passed through, we do know what its polarization is. So right now, I'm working on getting this thing running. So calibrating the camera, doing all kinds of tests to make sure it's good to go, because we're going to put it on the summit by the end of this year. I think that's the plan. So we're going to try to get this running pretty well here, and it's actually in this building, like down the hall. This is where we work, at the lab here. And then once we know how it's going to work, we're going to seal it up and send it to the summit, so we won't go inside it. And that's a vacuum chamber. That's also how we keep it cold. So I'll go over some of the questions that we can answer with this telescope, or just open questions in solar physics. So what we're going to look at with the DKIST telescope is the solar corona. And the DKIST telescope was designed to optimally look at the corona because it's an off-axis telescope, so that means that there's no mirror that's in front of the larger mirror that first connects the light. So it's going to be able to minimize the scattering of light that's from the really bright part of the sun. So you can just look at the edge. And the corona is the very outer edge there. There's lots of layers, as you can see, that we're studying. And something I recently wrote about with Jeff is a plan to study helium in the corona. So this is a picture of a spectrum, so it's like you get from a spectrograph. So you have a slit, you see the lines that show up at different frequencies, and one of them is helium. And our goal is to understand how this helium is produced inside the corona. And then if we can get a good understanding of how it's produced, we can start detecting helium and using that to understand other processes. Basically, that's what happens a lot in physics. Is like one thing that you're studying, understanding becomes the tool for your next experiments. So something we like to do, and something we can do with a smaller telescope that's already built, the Solar Sea telescope, is to just upgrade that a bit and try to look at lines, smaller lines along the spectrum where that helium line is, to really figure out exactly what atomic processes are occurring, producing the helium. And we also want to map out where this is happening within the corona. So the spectrum tells us about what atoms we're looking at, what is the source of the light. The polarization we can use to tell us what is the magnetic field, the surrounding magnetic field where this light was produced. So if we know where, what the polarization was, where the light was produced, or what the magnetic field was, where the light was produced, and we know where spatially in the corona that it's coming from, we hope to make a map of the magnetic field structure of the corona. And in the corona, there's a lot of plasma, which I mentioned is a fluid, but it is also dominated by electromagnetic forces. And there's some open problems in solar physics understanding heat flow of the corona. So we can't explain it using just thermodynamics. We don't really know what the magnetic field structure is, but it's hoped that the heat flow is really the result of magnetic forces causing the flow. So this is something that would explain a lot of phenomena in the corona, hopefully. And there's a lot of competing theories for the magnetic field structure. So that's it for my experimental work and experimental background. I don't know if anyone has questions right now that they wanted to ask about this topic before we move on to...
Can we ask them at the end of the talk?
Yeah, we can ask them at the end of the talk. I just didn't know if there's any sort of questions right now. So I'm going to be reciting a poem that I wrote for you guys called Time Out of This World, The Physics of Time, and How We Can Make Time Stand Still. This is about 10 or 15 minutes long. It's very technical, but hopefully it'll be entertaining. And it's not really challenging any established experimental work, but it's helping us to question ways we can understand scientific theories and interpret different competing theories. Strange, isn't it? If you start to think about it, what are we really? What's the fundamental nature of our experience? Physics makes the mundane strange, makes everyday occurrences mysterious. What hidden regularities lie within our reach? What are the patterns of nature? What mathematics do we need? A mathematical model of the universe. That's what physicists seek. But as a philosopher, I'm interested in what's beneath. The metaphysics within physics. That is what I seek. To read between the lines of mathematics, to have a metaphysical explanation, not just a useful mathematical equation. There's a philosophical problem in physics called the problem of the direction of time. It's a problem right at the intersection where physics and philosophy intertwine. My goal tonight is to argue that this debate is something that experiment can help decide, and that if one idea is correct, then for an isolated system, we can stop time. I'll first describe the problem and then some proposed solutions, followed by a result from a recent physics paper, and use it to argue how those solutions can be disproven. Now, consider, for example, the mechanics of Newton. To find the trajectories of objects, a spatial coordinate system must be chosen. Given the initial conditions, meaning the initial velocities and positions of all the particles composing the system, you know its whole trajectory, its whole future, its whole history. Use time as the variable, and you can find the positions of all particles at all times with certainty. Now, certainly, you know this only works in theory, because really, we don't know the initial conditions for a single speck of dust in this room. Better yet, for the entire universe in its entirety. Better yet, microscopically, which is what we really need to do if we wanted to reverse a physical system. Microscopically, there is reversibility. This is what we call time symmetry. Just plug in minus t, just a negative value of time into the equations of motion. It reverses the direction of the velocity, and you get the exact reverse trajectory. Each particle will end up where it began, exactly where you'd expect it to be. And now this really leads us to the question. Since the laws of motion are time reversal symmetric, there are so many more physically possible paths than expected. The laws of motion allow for miraculous happenings, things we've never detected. Things like an egg uncracking, like a broken glass unshattering, like a beer unspilling, like water unsplashing. The problem is that there's nothing in the laws of physics to explain why this weird stuff isn't happening. But for it to happen, you would need a very particular force on every single particle, somehow directed upward from the floor, somehow to make the broken glass spontaneously restored. But the spontaneous flow of energy like this isn't something that we see. It requires a decrease in entropy, the measure of disorder, of possibility, the measure of the possible microscopic arrangements beneath the macroscopic system that we see. This is all summarized in the science of heat. Derivable from statistical mechanics, this is the second law of thermodynamics, that the entropy of a system can only stay constant or increase if that system is isolated, meaning no energy enters or leaves. This is a law that establishes a direction of time because it makes irreversible processes well defined. It is possible for the glass to spontaneously recombine, but But this chance is so slim, it essentially doesn't matter. There are so many more microscopic arrangements compatible with the glass remaining shattered. But just counting a high number of possible microscopic states doesn't fully explain why the glass doesn't unbreak. There is something else that we need to postulate, which is that we can equate the probability of each microscopic state compatible with a macrostate, meaning the chance of each microstate happening is the same. Evolve time forward and it becomes probable that entropy will rise. But there is still a problem here because of the symmetry of time. Evolve time backwards and entropy will still rise, contrary to our experience, not something we want to hypothesize. This is what led philosophers to take the origin of the direction of time as something that originates at the moment of the Big Bang, at the moment of the universe's conception, where the fact that nothing existed before the Bang means you can only evolve time in one direction. And so in thermodynamics, the problem of the direction of time can be solved if you apply the postulate that the probability of each microstate is the same, only at the moment of the Big Bang, and then let time evolve. But now, consider the problem of electromagnetic radiation, in which charged particles emit light when undergoing acceleration. Consider mainly the argument that was raised on how time asymmetry arises from these waves. In his debate with Einstein in 1909, Walter Ritz argued that radiation is responsible for the observed asymmetry in time. Time's direction, in his theory, time's direction doesn't arise from probability. It arises straight from electromagnetic theory. If you're a physicist, this might sound confusing because the laws of electrodynamics are time symmetric, just like Newton's. Experimentally, we only observe light traveling from past to future. In the time reverse scenario, we should see light come collapsing in. But this is something we never see in the lab, and so in a theory, we assume a certain boundary condition. The rule of thumb is to neglect the solutions that go from future to past. They work just as well, but don't question it. Don't ask. Some would argue that that's a scientist's only task, to explain the data they see in the lab. Those neglected solutions are called the advanced fields. It's true, using them can feel really weird. It seems to violate causality and creates a strange picture of reality. It's like saying the future affects how the past will be. But actually, mathematically, for these types of equations, the sum of two solutions also solves it the same. You can solve the electrodynamics equations using a sum of incoming and outgoing waves. This might seem to violate your intuition, but it's just a description of waves traveling in superposition. Note that the sum of these solutions has time symmetry. Now, I'll describe the results of a recent analytical discovery made by Pardis Thikajati, recent alumnus of the University of Hawaii. She showed that the laws of electrodynamics are violated or energy is not conserved. She also hypothesized an experiment to look for the existence of the advanced fields, the fields traveling in reverse. And this would be a big deal, because it had been thought that the advanced fields aren't really real. I realize that this changes the debate on the direction of time, because some philosophers still argue against Einstein. For example, one philosopher of physics named Matthias Frisch argued that we should leave electrodynamics as it is. He says that there is no problem at all. Just take a time asymmetry in the radiation fields as a new fundamental law. Others disagree, of course, particularly philosopher Jill North, who argued that there is time symmetry in radiation, but the direction of time comes from probability, not the equations. If you're familiar with the arguments on how we observe the cosmic microwave background radiation, or the CMB, you'll see she argues similarly. Advanced radiation fields are just something we no longer see, sort of like particle physics interactions that only occurred when there was more heat. Back in the early universe, light could travel toward the past, but as the universe cooled and expanded, this process just didn't last. So Frisch's theory has already been analytically ruled out, but so in North's if Thikajati finds advanced fields in the lab. Something I should mention is that this is all about radiation to free space. But what about radiation that is confined? The study of radiation in a box actually won a Nobel Prize. In an experiment by Serge Haroche, he found in his lab the fields traveling in reverse. An accelerating particle only radiated when the radiation waves were compatible with the edges of the box. which caused a bit of a shock. It's like the box had an effect on the particle's internal clock. How did it know what the edges of the box were shaped like? It hadn't radiated yet, so there was no bounce back of light. The only explanation? The advanced waves traveling back from the future carried this information. Still, this discovery didn't catch on generally. It was thought that just in confined spaces did radiation have time symmetry. Now, I'd like to conclude with a hypothesis proposed to me by physicist John Mady, that perhaps we could stop time, maybe. You see, in Niknajati's paper, she favored a theory by Feynman and Wheeler, which is just as successful as these other theories, but wasn't taken seriously because it's weirder. If a tree falls in a forest and no one is around to hear it, does it make a sound? You can ask an analogous question here, and it's pretty profound. Will a particle radiate in empty space without bound? Or does there need to be an absorbing material around? Feynman and Wheeler answered no to this question. They assume that even in free space, for a particle to radiate, there needs to be a thermally absorbing boundary in the distance, or else no light will escape. Even if a particle accelerates, or rather, it just wouldn't accelerate, because in some sense it waits for information from those advanced waves from the future to tell it about the boundary's shape. Their theory is time symmetric, but the direction of time comes from, you might guess it, the probabilities in a thermally absorbing boundary in the distance. Maybe suggested, what if we put something larger than a single radiating particle inside a superconducting cavity, a cavity that inherently has no thermal absorption in its boundary? What if we put an amoeba inside? Would the amoeba age? Or would we stop time? What is the physical origin of the direction of time? A philosophical question, but one that future experiments could decide. And where my intellectual journey will go, I don't know, but I just let my memories of the future be my guide. So, lots of ideas there. Is there any questions on anything? Yeah.
I noticed that the title of your poem was actually a haiku poem.
No,
didn't even
you have
notice
to
that.
repeat the question.
Oh, wow.
Repeat the question.
Repeat the question for the recording.
So the statement was that she noticed that the title of my poem was itself a haiku, and I hadn't noticed that. I just thought it was a catchy title to get people interested. So yeah.
Are you working on CryoNurse now?
Yeah. So the question was if I'm working on CryoNurse right now, and the answer is yes. That's my job here at the ATRC, the Advanced Technology Research Center. That's where we are right now.
Are you able to pump the sarcophagus down to sufficiently low pressures in order to get the thermal characteristics you want?
So the question is, can we pump it down with vacuums to get the kind of characteristics we want? The answer is yes. We have it pumped down, and the goal is to get it running here the same way we running on the summit, so we know how it'll behave. So that is something we're doing.
Okay. Now with that, is the alignment of the optics stable within that from pump down or from cool down to cool down?
The question is, are the alignment of the optics stable from pump down to pump down, cool down to cool down? Not entirely sure. I think so. I know there's been some issues with mirrors having some damages that have been repaired. So,
But during the damaging process, is the alignment maintained?
right now we're pumping it down again because there was a power outage. So I'm not sure. Maybe the next thing once it is pumped back down, it's just.
Well, so you're right there at that information gap right now.
Yeah, I'm not really sure because I guess I've only been here for 2 months.
Now, when is CryoNurse expected to be delivered to the summit in working condition?
The question is, when is CryoNurse expected to be delivered to the summit in working condition? What I was told is that in the fall of this year, it's expected to be delivered to the summit.
Ooh, amazing.
Next question. Yeah.
When will the Advanced Technology Solar Telescope be open for business?
The question is, when will the Advanced Technology Solar Telescope be open for business? So I guess there's the Daniel K. Inouye Solar Telescope, which is probably what you're referring to. Yes? Yeah. Okay. So I think the data should come in 2020. We should start taking the first real data. Or maybe that's like the preliminary data, and then a year later we can get real science data. I'm not entirely sure. Sorry about that. Yes?
Yeah, could you tell us about some of the other experiments that will be done at the new telescope?
The question is, can I tell us about other experiments that will be done at the new telescope? So I'm guessing this is like questions about, because I mentioned the helium and other things people can study. So I know that understanding the magnetic field of the corona is a big goal. That's one of the main scientific goals. And a lot of scientific goals evolve around studying the corona. But I think there's many other things you can do with the DKIST experiment. That's what interested me the most.
May I assume that those other experiments will be done by other instruments other than cryo-NIRS?
The question is, will the other instruments on the telescope be doing different experiments? So the answer is yes. They'll have their own functions, so they'll have their own goals with what they can study.
And will those precede cryo-NIRS?
The question is, will those other experiments precede cryo-NIRS? The answer is, I really don't know.
Okay.
Yes.
Is there a difference in the atmospheric pressure when you do tests here versus what's up on the summit, and how do you factor that in?
The question is, how do we factor in differences in atmospheric pressure here at the summit? I know that it is going to be pumped down, so we are controlling the pressure inside the cryo-NIRS ourselves. So I think that should be enough to keep it at the settings that we want it to be. I don't know if there is anything special we do, anything different at the summit than we do here to count for that. If there's anything different besides just pumping down. That's it.
But this idea of the reversal of time traveling backwards, is that kind of explaining the cyclical universe where the Big Bang happened and the Big Bang will reverse itself in a cyclical fashion?
So the question is what I mentioned about time reversal, does it have to do with a cyclical cosmological theory of sort of a Big Bang happening in the future, like a cosmic crunch, I guess, that kind of thing? So the answer is that this doesn't really have to do with any cosmological theories. This is just questions coming out of just the mathematical nature of the time symmetry and laws of physics and laws of motion, and the idea of the advanced radiation fields. It's basically the idea that are configurations where we can, this hypothesis that we can do experiments to detect the advanced fields, the fields traveling back in the future in the lab, and they have been detected, like I said, in the Serge Hirosh experiment. So we do know these exist, and I guess maybe people like to imagine that this is like things are happening very different. It's just like a different conceptual understanding of what's fundamentally happening through radiation, just a better microscopic picture of what's happening near the particles, that the advanced radiation fields aren't canceled out, and that they're playing a role in phenomena that's happening all the time. Like we've had to have successful, like established science at different energy scales, or just how finely you can look at the oscillating charges to look for the advanced fields. So it's basically conceptual shape.
Have you thought about the idea of time reversal in a biological system such as photosynthesis?
The question is, have I thought about time reversal in a biological system such as photosynthesis? I haven't really thought about that. I guess the idea of putting the amoeba inside the superconducting cavity is something that's basically an analog to the Serge-Haroche experiment, except instead of putting particles that, just single particles that are radiating, putting in something that's more complicated. This is like an ultimate test of the Feynman-Wheeler theory. Like, if you have something that's totally reflective and not going to absorb anything, you could test out if a particle will radiate. And if there's no radiation in that space, if that's confined space with no thermal absorption, the next idea would be can things age inside it? Because that would be a way of trying to figure out if maybe fundamental laws in electrodynamics are the origin of the direction of time, or whether it is involving all the statistics of particles in a thermally absorbing boundary. And I guess I had some really
my thought here is that biological processes are often mediated by enzymes that are unidirectional. They only go in one direction. So what would time reversal say about biological processes that are driven by enzymes that only drive in one direction and go the other direction?
The question is, what would time reversals say about biological processes that only go in one direction and not the other? Is that a good summary? Well, there's so many biological processes, like all this aging, that have a direction of time. Everything we experience, like computers can break, drop a dish, everything that we do, there's a direction of time. Just the fact that we have memories of the past and not the future, these sorts of things, we experience a direction of time. So things like the enzymes, I guess that sounds like just a microscopic, just a smaller scale of the direction of time we're experiencing in our lives. That's how I would see it. It's just maybe not as big as a human being, maybe at the level of like an amoeba, but something that has a direction of time, but it's still too big and has too many particles to say it's like as fundamental as like the single radiating particle. So the idea is the radiating particle is different than the thermodynamic explanation because it involves one particle emitting a photon. So there's no statistical mechanical explanation for one particle. It only has observed one direction of time. So that's how this kind of led to this debate with Einstein and Ritz that radiation could maybe be something that's really the root of the direction of time and not the statistical explanation. Other questions? If JD is here, if we